start the show. Okay, I'm gonna be tethered to the desk here. Maybe I'll rotate it here as I try to point to the screen that we see here presented. And then I'm gonna duplicate slideshow. There we go. Okay, kind of in the way here though. Oh boy, what happened there? Okay, all right. Now I don't want you to write any of this down. As a matter of fact, can you turn off the lights completely? Just because this is an older PowerPoint and I didn't really probably do a great job with the fonts. Sure, yep, get them all the way off. Oh, nice. Okay, dark and scary. But I wanted to to do exponents, or I'm sorry, reverse that. To do radicals, you have to know your exponent rules, and hopefully you did do this last year. But back in the day when I first taught it, I broke it down. So the first ones are just like multiplication property of exponents. 3x to the fourth and 4x squared. I really wrote this out um, extravagantly here. I wrote out all of the x's. Okay, I think I do this in the next one, and this is why I wouldn't want you to write this down. So that's called a commutative property. I'm able to take 3 and 4 and multiply them. I can reshuffle the multiplication. And then I really broke down why I do what I do with x to the fourth times x squared. X to the fourth is 4x's. X squared is 2x's. How many x's are multiplied together now? Say it. 3, 2, 1, go. 6. And how do you write that? X to the sixth. So it's 12x to the sixth. So what do you do with the exponents, everybody? You add them. But that's because that's how many x's are multiplied together when you're done. The reason behind things. A lot of times I get my cat students flipping coins. X to the fourth times x squared is x to the eighth. I multiply the exponents. No, you reverse the rule. You're not thinking. All right. And that's why I did all this. All right. I kept this as negative exponents, I believe. And then I'll tell you where the right when I actually get into the notes. Oh, and I did realize now in the middle of my tape, I think I forgot to do something. Oh no, I did. I think I'm good. But shuffle, and then okay, what do I do with the exponents? I add them. What's negative 2 plus 7? 5. But really, what happens? X to the negative second belongs on the bottom as x to the second, and then just humor me. I have 7 x's on the top and 2 x's now on the bottom. How many cancel? 1, 2. That's how I get x to the fifth as well. So that's what's behind the negative exponent rule. And then I think I really get nuts with this one. You want to get nuts? Let's get nuts. This is why you do what with the exponents? You add them because that's how many x's are being multiplied together. So I did this as a educational idea of why we do the things that we do. The next one, x to the third raised to the fifth. That means x to the third 5 times. If that's x to the third 5 times, that's that many x's multiplied together. How many x's are going to result here multiplied together? 15. What do you have to do with 3 and 5 to get 15 fast? Multiply. These are the reasons. Ah! You see that? It just disconnected. This happens like 3 times a day in my third period. I think someone's sabotaging me. I think someone has a button in this class. Who did it? You guys seem to be happy back there. Did you guys do that? Okay. What's your device you have in your hand? Is that your phone? You put that phone away. You probably got a device that could disconnect me from the thing. Did I say good morning, by the way? I forgot this is third hour. Y'all look like you want to kill me right now. Sorry. I don't know what I did to you. All right. Next one. Okay. Boom. Okay. There it comes. Final answer. Multiply the exponents, but you'll have to change that to 1 over x to the 10th for a final answer. I just didn't do that right now because I technically did not do the negative exponent rule. And then this one, okay, fine. The rule is multiply the exponents. But I do believe I changed this one, though, I think. Oh, I hit that. Where's it at? Nope, I didn't. That should have been that. I think it was y to the 10th. On the top negative, it should have been over y to the 10th thrown on the bottom. Okay, now I'm going to move myself again. Now you want to get nuts? Let's get nuts. This is, and I wish I would have put this one out more, but I didn't. I wanted to write, if I would redo this, I'd write this as 4x's multiplied up on the top and then 1x on the bottom. One of them cancel. Or you can do the subtraction rule of exponents. 4 minus 1 is 3, but that's what's really happening. The things are canceling. Letter B can be approached a couple different ways. And by the way, you do the numbers separately. 8 divided by 2 is 4. So hopefully you did this last year or in grade school, a little bit of fractional work with radicals. I'm sorry, not radicals, exponents. Negative 3 over 15 reduces, but you can do one of two things. Subtraction rule. 4 minus negative 6 is x to the 10th, or take that x to the negative 6 on the bottom and put it up on the top. And then you have x to the 4th times x to the 6th, add the exponents. One way or the other, that's what we need to know there. And then this one, I'd like to do this, and I'm going to write it when I actually tell you to write notes down. How did I get x to the 3rd on the bottom? I can't really go up there, and I can't really write on this PowerPoint anymore. I lost that ability, but you have x to the 4th. That's what my 4 fingers are. 4 fingers. You can't see me probably over there. I moved that mouse in front of that exponent. X to the 7th. What you got to visualize is 4 of the x's cancel. Where are there more x's? On the top or bottom? 3, 2, 1, go. Bottom. So that's why that's x to the 3rd on the bottom. But we have this thing we can do where we could subtract exponents. What's 4 minus 7, everybody? 3, 2, 1, go. Negative 3. So x to the negative 3rd on the top is x to the positive 3rd on the bottom, because this subtraction of exponent rule of exponents has created this problem, has created the negative exponent conundrum. Z to the 4th over z to the 4th is 1 over 1. That's why you don't see any z's anymore. I'm really concentrating on c up at the top there. All right, and then talking about the negative exponent rule, just the action of it. All right, so this one is the y to the 3rd should go on the bottom. This one is actually a total flip-flop. X to the negative 7th on the top is on the bottom now as a positive. Y to the negative 5th is up on the top. And I'll explain this when we get into the notes here. And then 3 to the negative 2nd, we already did that without a calculator. 1 over 3 to the 2nd, which is 1 over 9. What's anything to the 0 power? 3, 2, 1, go. 1. That is created by, yet again, the subtraction rule of exponents. All right, to simplify things that are in that fractional component there. And then the last page is product raised to a power. Basically, you distribute this power, but look at how I break down the first one. What something to the 3rd power means is something times itself 3 times. So that's really what that means. That's why I'm going to take 3 to the 3rd power and get 27. That's why I'm going to take x to the 4th to the 3rd power and multiply those exponents. Y to the 2nd raised to the 3rd power. So this is the reasons behind this stuff. And then we're going to go quickly. 5 squared is 25. X to the 5th squared is multiply those exponents, x to the 10th. Then y to the 6th negative squared is y to the negative 12th. Then you flip the y. The y has to be on the bottom. Actually, a rule, you should never leave a negative exponent in the final answer. All right, so kind of felt like we had to go through this in order to be ready for some radical things that we're going to do. So square 3x to the 4th, cube 2y to the 3rd, then use the commutative property 9 times 8. PEMDAS, exponents first, then, and then here you are doing your homework, but we're not ready for that yet. Oh, why did he stop moving? Didn't you see his legs move? Anyone see his legs move? All right, there they go. All right. Okay, so we'll end that, and then we'll actually go into the notes that I want you to write down. Okay. I think they're just mad that I put them in rows. Okay, where am I at? Did I do this? Is that the guy? It looked like, oh, never mind. Okay, that's one I did do. All right, so come back up here. All right, now put my face up in the corner here. Yeah, shrink it down. Yep, that's as small as it can go. All right, remember, you don't have to. Okay, let's all say it. I can, I can, I can. Come on. I can, I can. Third hour. Man, rough. All right, vocab, radical expression, rational exponent, like radicals, and reduced radical form. This is going to be a big one today. And I don't know if I'm going to get through all the notes. You need to be ready. Hey, can you turn that light back on now? I just wanted that to pop a little bit more. Just the font was too small. So I feel like with the lights off, we can see a little bit better. This should be better. Okay, I can produce a reduced radical for expressions. Do remember this? This is going to come into play maybe once or twice, knowing that square root of n is equal to a to the 1 over n. All right, and it is a 1 there. And then simplifying. So now go ahead and write this down. A simplified form of the big, long, convoluted thing I just showed you, the y's. Can't flip a coin. Flip a coin, you're wrong 50% of the time. That's an F. All right. So we got to understand a squared times a to the third. That's 2a's and 3a's multiplied together. That's 5a's. I add the exponents. All right. The quotient rule. Really, what you should do is determine where are there more a's. And there are more a's on the top. If I listed all the A's out, that's what I really should have done in that PowerPoint is shown A over A, and then show the cross out of the A's. And then, oh, I have more A's on the top and there's 3 more. So A to the third. So that's why we can subtract. It just tells us the difference about how many A's are where. Power raised to a power, multiply the exponents. Power of a product. You take the product, all parts of it raised to a power, not a sum, not a sum. Remember, I had you bums. The bums that we had this earlier in our first chapter. I guess we'll call it chapter 1. X plus 1 squared. Let's say x plus 2 squared. And I was getting people writing x squared plus 4 on this, distributing the power. That is not true. What are you supposed to do with it? It starts with an F. 3, 2, 1, go. Foil. You get a middle term, so that's a not equal. It is actually valuable to cover that right now because I get people still doing that. You're gone. That's an F student right there, especially in honors. We can't be making those mistakes. All right, now I'm really going to break down the negative exponent rule and tell you how the quotient rule created this conundrum. I'm really going to zoom in on this, then I'm going to zoom back. Boom. This could theoretically come from this question. A to the fourth, let's say, over a to the seventh. What I've always told my students when we had this specific section, which we won't, I just feel like I have to do this because radicals are a form of exponents. It's actually true. I've always told them, just tell yourself, where are there more A's? Where are there more A's, top or bottom, everyone? 3, 2, 1, go. Bottom. And then just go ahead and cancel them. I actually told my students in the past, subtract and reverse. Do 7 minus 4 and just know the answer belongs on the bottom because there's more A's multiplied together on the bottom. But then the robots, when you do the 4 minus 7, that's a to the negative third. Well, that's the creation of the negative exponent conundrum. You must know then that there really are more a's in the bottom, so a to the negative third means 1 over a to the positive third. So this created the negative exponent conundrum. It also created the zero exponent conundrum, because theoretically speaking, this could have came from a to the sixth over a to the sixth. I'm just making up some things. First of all, what is something divided by itself always? 3, 2, 1, go. 1. But if you are robotically using the zero or the quotient power rule, quotient of powers, and subtracting, this is a to the 6 minus 6, which is a to the 0. Well, the only way that could result is if you divided something by itself, which means that equals 1. So I always love covering the why, then people have a firmer understanding of the what. They can actually do things better. Okay, and remember better. Okay, now these last ones, I guess you can write. I feel like that first row isn't needed. Radical expression, an expression with a radical. Okay, great. Sounds like a redundancy. But really, the big thing is this. We are going to reduce radicals today, and all the forms I think we could possibly run into. So it's going to be a big day. So here's what has to happen. You can't have roots that are left to extract. You've already got marked wrong for this for the quadratic formula. If you wrote square root of 12 as a final answer, that is not reduced or simplified. 12 is 4 times 3. The square root of 4 should have been a 2 out. You cannot write square root of a negative as a final answer. What are you supposed to write instead? 3, 2, 1, go. I number. So I ding people for that because it's unacceptable. We had too many examples where the key had I in it in every answer. So those that are not doing your homework appropriately and then also not checking the keys, those are the ones that do those mistakes. That's why I hammered down, it was actually specifically this class. All the non-perfect homework people had a D average on that particular quiz. It's the truth. All right. Now, here's examples of reduced radicals. There's nothing I can do. Square root of xy stuck. And that's what's going to happen today. You're going to get radicals that don't work out perfectly. All right. But, and then we're going to have leftovers stuck in there, I like to call it. This is good. And then here's a weird math thing. You can never, ever, ever leave a radical in the denominator. All right. That's a weird math thing. It actually creates a process called rationalizing a denominator, which is a skill that's needed in higher level math classes. So you just have to trust me on that. So then over to the right, here's examples of not simplified. I want to zoom in on that. This is not simplified because fourth root of x to the fifth, there's enough x's to free an x out of here. And I'll show you how to simplify that today. You probably already have an idea. But that's not simplified because there's more that can come out of there. And never can you leave a radical in the denominator. That'll be dinged as a final answer. But I have to show you what to do on that one in order to get it simplified. Okay, so that's what we're doing. And then there's more to this, but those are the general ideas. Never radical in the denominator. Every single radical must be simplified all the way through. All right. And then we have a bunch of different processes of that happening. Okay, and I'm going to write some things down here, but we are going to talk about that absolute value thing as well a little bit, only for the first couple. I felt like I did hear a door open. Yeah. How's it going today? Who are we playing today? Oh, that should be easy, right? Victoria. There you are. Sorry. We didn't say your last name. All right. So it said when convenient. Probably not right now. Probably have to wait till the end. All right. So moving in. Oh, yeah. Okay. And then one more thing. You don't maybe have to write this down, and I'm barely going to use the fractional exponent rule. As a matter of fact, one of the examples I did first hour, I'm deleting it in your hour. I don't think we need it yet. But I'm going to liberally go back and forth on this. If I have a square root of a product, I'm going to break that sometimes up into two separate radicals as a product. And I'm definitely going to do that with the fractional situation. I'm going to liberally go back and forth with square root of a fraction equals square root of numerator and square root of the denominator. There are times, this is more Monday's stuff, that you need to change the radical into a fractional component and then go from there. There are 4 questions in your homework. I say it on the calendar. Leave that as fractional exponents and do some exponent rules. Okay. And hopefully you can handle that. Okay, so here's a for instance on 19 through 22, I think, is what those are. What would I do for x to the 1/2 times x to the 1/3? First of all, what's the rule? What do I do with the exponents? I'll give you a 50-50. Do you add them or do you multiply them? 3, 2, 1, go. Add them. When it's x times x, you add them. How do I add fractions? I need a common denominator. This would be 3/6. This would be 2/6. So this is what we want to do on those numbers. It's the only ones that we're going to leave it as fractional exponents and use our exponent rules. That's why I had to cover our exponent rules today. I don't know if you know them. I think you do, but I don't know. So even if you do know, we need a refresher, right? So that's why that's done. I didn't even do that first hour, but I looked more into the book and saw the assignments and just wanted to make sure. So very few of them you will do this. All the rest of them are all in radical form. All right, we're halfway through, not even, right? And we're not even halfway through the notes. We haven't even done an example yet, right? So that's where we're at. All right, you guys ready? Should we get up and do some jumping jacks? No? Make sure we have some energy. How's that gum over there? Good? Lexi Samuelis just got a detention for chewing gum in school. I just thought I'd share that. All right. Used to be a rule in high school as well. You know why? Because the jerks, you know what they do with their gum? You know what they would do? Right under the desk. When I was at Providence, I'd gum all over my desks, all over. All right. So I guess kids these days are a little bit better than those bums from the past. Probably should write these down. I think the hardest one maybe to remember is the 216. What cubed equals 216 then, just by this progression? What do you think? 3, 2, 1, go. 6. I think there should be one more that you should write, like 1,000, right? Everyone should know powers of 10. It would be helpful, in these things. I think everything else should be good. You should know 1, 8, 27, 64, and certainly 125. And then for fourths, maybe, I'm not going to do fifths because when we get to the fifths, we're probably going to have only like 2 to the fifth, which is 32, a little bit tougher. All right. But fourths, we should know 1 to the fourth, 2 to the fourth, 3 to the fourth, 4 to the fourth is another one that's tough. Do you remember 4 to the fourth? 2, I've written this twice, 256. This one is also a tough one. That's probably the 2 toughest. But this is not. 5 times 125 is 625. And then I'll stop there. Oh, no, I won't. 10,000. And so on, any power of 10 should be simple. Okay? Should be simple to deal with. Okay, so all of those I think are reasonable to remember those. Okay, now here's the difference today. This is why I switched what we did last year. Last year I did this a day later after what you did yesterday, and this more coincides with what you did yesterday. Yesterday everything was perfect. Everything was perfect. Today it's not. 54 is not a perfect cube. So here's what you got to do. You got to start breaking these down. Well, the first thing I might try is 2. 2 times what? Is 27 a perfect cube? Yes or no? 3, 2, 1, go. So that's what I said about liberally. This is what I'm going to do, but I'm never going to write this like this again. Cube root of 27 times the cube root of 2 times the cube root of y squared. What's the cube root of 27, everybody? 3, 2, 1, go. 3 is out. 3 is free. The evaluation of cube root of 27 is handled. Everything else is stuck in jail. So I have to make that cube root of 2, and then y squared is a perfect square, but it's not a perfect cube. So it is not enough y's to free a y, is the best way. Sometimes I call that the jailbreak method of radicals. If I have a cube root, I need 3 y's. I don't. I'm done, right? Not even asked, do I need an absolute value around a 3? It never happens with a number. By the way, why is an absolute value not even in play? That index is 3, 2, 1, go. Odd is what we should have said. Odd. Okay, so that's that silly rule. And then I'm going to do an absolute value possibly on this one, and then we're going to be done, and I'll tell you when that would happen. I'll put it in the appropriate place. First of all, is 81 a perfect fourth root? Yes or no? 3, 2, 1, go. Yes. So I'm going to leave 81 for a minute. I'm not going to write this as separate 4 radicals, but I am going to separately evaluate each radical. And I'll show you with the highlighter what that means. By the way, from yesterday's notes, is a to the 8th a perfect fourth root? Yes or no? 3, 2, 1, go. Oh, no, you didn't do your homework yesterday? Let's ask one more time. Is a to the 8th a perfect fourth root? Yes or no? 3, 2, 1, go. Yes. Okay, so I'm going to write a to the 4th there. And I'll just hold for a minute. Now b to the fifth. Is that a perfect fourth root? Yes or no? 3, 2, 1, go. No, but I need to break this down, and this is why I went over the exponent rules. I need to break this down into a product that is, and then the leftover. So I got to break down b to the fifth to b to the fourth times b to the first, reversing the sum rule of the exponents. Okay, now I can ask all of these individually. What's the fourth root of 81, everyone? 3, 2, 1, go. 3. What's the fourth root of b, a to the fourth? 3, 2, 1, go. I'm sorry, that's an 8. That's an 8. Is that why we had our hand up? My bad, dogs. Ruff. What's the fourth root of a to the eighth? 3, 2, 1, go. A squared, divide. And then what's the fourth root of b to the fourth? 3, 2, 1, go. B. And then what's stuck in jail? This is a really smart way to write this. Write a times, and then write the fourth root really attached to that radical. Because otherwise, if your 4 is floating, I might think it's on the B. All right, so get that fourth root on the radical. Okay, now I think in these questions, this is kind of, well, I won't say anything more, but for the absolute value rule, does 3, a squared, b, or none of them require an absolute value? I gave you 4 choices. 3, 2, 1, go. B. How many people said B, but barely? Okay. An even power resulted in, an even index resulted in an odd power. But then I got a problem with this. If B was negative, what's the fourth root of a negative? What's the fourth root of a negative? An I number. And B is still stuck inside there. So that's why the absolute values on these kind of questions, I don't really like them. So here's what people usually do on the directions then. They write this added thing. Go ahead and write this down. And really the directions could just say simplify. That's it. But then they add this little caveat. That's a little extra additional term here, an additional thing. Assume all variables, they really should say represent. Assume all variables represent positive numbers, or they just say are positive. What that does is relieves you of the having to think who deserves an absolute value. Once we say all the variables are positive numbers, then I couldn't care less if we have an absolute value on there anymore. So it relieves you of that thought process. This is a very common thing right here to add the directions. All right, so then we don't have to do that. So we'll do that from here on out. Okay, 128. Is that a perfect fifth root? I'm going to break this down. 2 times 64. Wait a minute. Now I'm getting somewhere where I kind of know. I know 64 is 2 to the 6th power. Because I know if I divide 64 one more time, this is the 4th or 5th time in 2 days that I've seen 32 in a fifth root. Okay, so here's what I do. Now I'm going to write this. I'm going to write this as fifth root of 32 and then times 4, because that's still equivalent to 128. You're going to find that the number part for simplifying is the worst. Variables are going to be really easy. Okay, the number part and getting this broken down so we can get a perfect, in this case, fifth root is going to be the hardest. Okay, and it's really just because of numeracy. Because x to the 6th, what am I going to write for that, everyone? I'm going to write 2 different x's here. What's the power going to be on the first one? 3, 2, 1, go. 5. No one answered. That means we're not getting it. What's left over? How many more x's do I have? What's the other exponent? 3, 2, 1, go. 1. All right, and then do I have to do anything for y to the 10th? Yes or no? No. And then sometimes I circle because I don't want to keep grabbing the highlighter. These are all perfect fifth roots now. Those are who get to come out. Those are who get to be evaluated. What's the fifth root of 32, everyone? 3, 2, 1, go. 2 out. What's the fifth root of x to the 5th, everyone? 3, 2, 1, go. X. What's the fifth root of y to the 10th, everyone? 3, 2, 1, go. Y squared. And then times the fifth root of who's stuck in jail, like some students feel in Mr. Samuelis's class. Out, in. Okay? Got it? Have you ever done this before? Good. I have value. I'm doing something for you. Oh boy, get ready for this one. Are you ready for this? Boom, 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 boom. Here's our first question where we have a radical. So actually off to the side, write this real large. Get a real special section for fractions. Everyone hates fractions anyway. All right. So what I can't have is a radical in the denominator. That's what I cannot have. So I've created this one thing way back in the day. It's like an infomercial. Root it, reduce it, or rationalize it. These are the 3 R's we should think of when we see a fractional radical with variables and all, or even without variables, just numbers. So root it, reduce it, rationalize it. This is what I mean about, and actually root it and reduce it should not be 1 and 2. These are like together. I should almost call this step 1. Try to root it or reduce it before you try. You don't even know what rationalize means right now. As a matter of fact, in this one, it's not going to happen. Well, actually, I kind of disagree with myself. I think you should think about reducing first. Because does anything reduce? Who might reduce within this fraction? You can ignore the cube root for a second. What letter? 3, 2, 1, go. X, right? How come no one's saying anything in third hour? You're scaring me. So let's all say this together. Who reduces? 3, 2, 1, go. The X's. We can speak. It's amazing. All right. And what will happen through our subtraction rule is that this will be the cube root of X cubed, Y squared over just 125. Oh, actually, what I should have done is this. Maybe I should just separate these and think of these separately. And I said I would liberally do that. A cube root of a fraction, I can take the cube root of the numerator and denominator separately. Done reducing, does anything root perfectly? 3. What roots perfectly? 3, 2, 1, go. What number? 125. Correct. And then guess what you took care of without having to rationalize? You no longer have a radical in the denominator. Through reducing first, and then that being a perfect cube root, you've accomplished that silly rule that mathematicians need. No radical in the denominator. By the way, there's one other thing. Roots. What variable? 3, 2, 1, go. X. And then I couldn't care less if there's a radical in the numerator. There are, you just have to wax on, say it. Have I done that with you guys? Wax on, anyone? Wax off. That's a Mr. Miyagi. Why am I doing this? So I go, yeah, and actually be a good karate blocker and whatever. But this is a skill that is needed in calculus. This whole idea of rationalizing a denominator. Anywho, let's move on to products. Basically, this is all long-winded. This could just say simplify, and then it'd just be a lot quicker. Okay, that's all it would be. And this is the one I'm not doing. I'm not doing it because I don't think it ends up in the homework. I might look at this Monday. All right, but this one I am. Remember I told you we could go back and forth with a fifth root times a fifth root. I can write it all underneath 1/5 root. But what I got to do is find a perfect fifth root in here. By the way, 16 is 2 to the, anyone? 2 to the, anyone? Fourth, I should have said 3, 2, 1. So what I'm going to do is borrow a 2 from this 8. Oh, and now I can think of this as 32 times 4, which is equivalent to 16 times 8. Okay, everybody, what is the fifth root of 32? 3, 2, 1, go. 2 times the fifth root of 4 stuck in jail. Not the square root of 4. 4 doesn't have enough factors to get out of a fifth root. The 5 means something times itself 5 times. That's only 2 times itself twice. Okay, so I am slowing down because I know you have to write the question because I didn't give you or supply you some notes. Okay, so really the directions for all of this is just simplify. You know what you should also add from this point? Assume all variables are positive, so I don't have to worry about the absolute value thing. You're gone. Here's the big problem with this one. These indexes are not equal. This creates a huge conundrum. What I have to do with that is turn that into a fractional exponent and do some crazy stuff. That ended up being a 6-stepper in my other hour. What this is going to do is actually save us some time. I'll be able to cut into more questions that you don't have to watch a video as much anyway. So I think this is what I ended in first hour. So after this is a bonus. And then I'm going to tell you to refer to the second video that I have online, and then pull until we get to the point where you missed the stuff. Okay, it's still root it, reduce it before rationalizing, the 3 R's for fractions. But does anything root? Do you see any perfect cubes? Yes or no? Don't shake your head. Shake your head this way, because this is a perfect square that doesn't come out of a cube root. Does anything reduce? Does 2 and 9 reduce? No. N and M? No. So now we're stuck with rationalizing. By the way, I'm going to help you with this one a little bit. I'm going to separate this as the 2 separate cube roots. That's too big. So start over. I just got that word rationalize in the way. I don't care about the numerator. I care about the denominator. By the way, what's 9? What times what? 3, 2, 1, go. 3 times 3. And this is always hilarious. What's the cube root of 3? And I get some people say 1. No, that's 1 plus 1 plus 1 is 3. 1 times 1 times 1 is 1. All right. So I have 2 3s and an M. Okay, now I have a question for you. In a perfect world, how many 3s would be in the denominator so that it would simplify? How many 3s would I need? 3, 2, 1, go. 3. How many M's would I need? Same answer. 3. Make your fantasies come true. Take the numerator and denominator and multiply it by the same thing. First of all, the reason is that green equals 1 then. When you multiply something by 1, you don't change its value. You just might change the way it looks. It's just like a common denominator with fractions. 1/2, you multiply both top and bottom by 2, it's now 2/4. Same thing, but I multiply by a form of 1. How many 3s did we want on the bottom? Say it again. 1, 2, 3. 3, or 3, 2, 1, sorry. So how many more 3s do I need? How many more do I need? 3, 2, 1, go. 1. So 1 3 goes in here and here. And how many M's did we need? 2 more, because we needed a total of 3. So M and M. M&M's. Actually, I don't eat candy, so. And then just to really clarify this is a useless step. And then I told you I was going to do this. 3 times 3 times 3, M times M times M is now on the bottom. Up on the top, we got cube root of 2 times 3 times M times M times N. I told you I was going to liberally go back and forth between writing 2 radicals into 1, as long as the indexes are equal. And then everybody, what's the cube root of 3 3s? 3. What's the cube root of 3 M's? M. You've accomplished no radical in the denominator. Whip-de-doo. But it is something we need to do. Up on the top, this is a 3, sorry. You go ahead and simplify because nothing comes out in the top. And no, you cannot turn around at the end here and cancel this 6 with this 3. Cube root of 6 does not mesh with a free 3 on the outside. This is done. It is over. All right? All right. Okay, so again, this is probably the worst thing that you have to run into. Well, there's something even worse. What time do we get out of here? Is it 05? Oh, I have an eternity. I have a lot that I can do. So the video that I have online for the next miss part, we're not going to do that one. I think I start off with this one. So when you open up that video, whatever I don't finish, you have to look at. It's 14 minutes long. You may only have to look at 8 minutes. And if you don't look at it, that's how I feel about you. 8 minutes, you're going to spend 4 hours over the weekend on this device. And that's a conservative estimate. I'm holding up the phone. All right. So can you give me 8 minutes maybe? All right. Maybe that would be nice. All righty then. He's so mean. No, I'm a realist. I know what goes on out there. I have 3 daughters. They lay in their bed like mummies and they sit there with the phone like this. It's like, I just want to, you know what? Would it be better if I got something attached to yours that would just hold your phone like this? So then you could just do this. Like, okay. I'm glad this is on the video. This is the world we live in right now. Am I making you guys mad? Anyway. Hey, what's 16? A number. 16 is 2 to the, say it, 3, 2, 1, go. Fourth. Oh. So it's just not enough. And then x to the third, we're going to write as x to the third. So what do you surmise I'm going to multiply top and bottom by so that I can get a perfect fifth root on the bottom? Let me rephrase that answer. How many 2's do I need added? 3, 2, 1, go. 1. How many x's do I need added? Say it. 3, 2, 1, go. 2. And I'll write them as x and x. You can write it as x squared if you want. And both top and bottom. I hope you parents do see that video, this video, and hear what I say here. Because this is the big problem. Those phones have destroyed education. That's why we no phones. Put your phone away. Put your earbuds away. Put your phone away. Got drones in the hallway, nearly running me over because they don't even know I exist because they're walking down the hallway like this. To the fifth, x to the fifth. I almost put n m. Now this is a useless step right here. If you understood what you did, you don't have to write the second step. All I would have to see is that rationalization part, and then understanding that that's a free 2 and a free x. And then up at the top, nothing is a perfect fifth root, so nothing cancels. And then yet again, no, you don't cancel the 14 and the 2. You can't cancel the x squared with the x because one's in and one's out. Those don't mingle. So that is the ugly, disgusting looking final answer. It doesn't look great. I'm just being honest, but at least you got the radical out of the denominator and you understand the rationalization process. Okay? Okay. All right, where are we at here? All right, and then again, this was probably like 3 minutes of my 4-minute video. I didn't get to this part, so I had to explain this in the video of what happens next, and then so there's going to be a little bit of overlap. All right, so what are like radicals? Here's an example of like radicals. You have an equal radicand, that's the number on the inside, and you have also equal indexes. And I gave a little example of this compared to algebra. Everyone knows 3x plus 4x equals 7x. Well, that is related to 3 root 2 plus 4 root 2. The root 2's are like these x's. They're like terms. So how do you add them? You get 7, and it's just root 2. Just like 3x and 4x is 7x. Nothing happens to the x. It's just they're like terms. So some people try to make that 7 root 4 or something. They make up a math. And it's not true. Another example of like radicals that I added, I think, in the video was after looking at the bottom, 3 root xy plus 2 root xy. Now we really got variables here, right? But when you have radical variables, and those are exactly the same, equal indexes and equal variables on the inside, then that is a like term. Can't think of any others. I think you get the point. So on the bottom, I did get a complicated one. Here's an example of like radicals. I guess redundant. That was a redundancy. Cube root of 2xy, nothing comes out, plus 4 times the same cube root of 2xy. That's now 5 of those cube root 2xy's because there's a 1 in front of this. 1 plus 4 is 5. And then an example of not like radicals. Root 2 plus root 5, I get goofballs saying that's root 7. That doesn't happen. And then if you don't have the same index, then those cannot be like radicals. So just have that in mind as well. Where are we at here? I'll probably end on this one. And then that means you're probably about, like I said, 8 to 9 minutes on the other video. All right. And then I'll replace my old video with this one that's on the calendar right now. Now you got this long expression. Square root of 20 minus cube root of 16. I shouldn't have to reread it. We got running short on time. What you got to do with this is simplify each one separately. And because of time, I got to go. So 20 is 4 times 5. What's the square root of 4, everyone? 3, 2, 1, go. 2 root 5. And then this is 8 times 3, or 2, sorry. And then I'll circle the perfect cubes and squares. This is often how I do this when I have a test. I start doing the work right there and not rewrite the question. And then what's the cube root of 8, everyone? Yet again, 3, 2, 1, go. Cube root of 2. I'm fine. And then 250 is 125 times 2. What's the cube root of 125, everyone? 3, 2, 1, go. 5. And then the cube root of, or square root of 5 is just the square root of 5. Oh, then after doing this, these two are the exact same. What's 2 minus 1, everyone? I don't know. Let me get my calculator. 1 root 5. And then negative 2 root 3, cube root of 2. And 5 times the cube root of 2. What's negative 2 plus 5, everyone? 3 times the cube root of 2. So this is where this comes into play. All right. And then, like I said, watch the other video. I'm shutting this sucker down. So I got a little bit farther and was able to explain that.